We're moving into integration, right? So we've covered the ideas in calculus of differentiation and integration already. We have them in our minds. So having worked out how to differentiate exponentials, we can just go straight into integrating. We don't need to learn any new lessons, okay? Everything we know about integration is founded upon what you already know about differentiation. So each of these is a statement that we've already established, and we have a corresponding statement in integration that we can conclude on the basis of these corollaries that we're talking about. Okay? So, since by definition the derivative of e to the x is just e to the x, right? That means that the integral of e to the x, if you're just reversing the process, is going to be e to the x with our constant of integration, right? If you have another base, then some long terms are going to get in there. We can get to that. I didn't write that on the board, but we can. So you can see here, because differentiation and integration, they're kind of like a valve, right? Once you go through, you come back the other way, you don't know what that constant was. In this case, it was 0. But it could have been 2 or 3 or 500 or pi, etc. So we'll just have our plus c, okay? Or some mysteries long term if you like. Okay? Here you can see, if I've got a linear function in there, so a very, very simple kind of function, you can see that the derivative has come out the front. So this is just like the simplest version of chain rule that you could possibly do, right? So the derivative of your inner function, your inside function is a, that's why it pops out the front. Okay? So then, if I'm integrating this same guy, just like with when we were doing anti-differentiation for polynomials, right? Instead of multiplying, I am going to divide. And of course the constant comes along for the right. Okay? One of the great things about this is it's very easy to verify. Okay? We've got differentiation right in our heads. Okay? So we can just give this a go. Oh yeah, this a will come out the front, cancel, and you're back to exactly what you were hoping for. Okay? Last one, just to generalize this pattern a little bit further, if it's not ax plus b up the top, just some other thing. Okay? If you see out the front of your exponential function you're trying to integrate, if you see something in this form, or something that isn't too different from it, then you know what you're going to integrate up into was this. This is where you came from, right? And this is where you ended up. So you're going to get your e to the power of fx plus c. Okay, and again, you can differentiate to check. So just looking at some very brief examples, I don't need to give you much of an example for the first one because it is its own example, okay? But looking at the second one, have a look at this, okay? If I'm integrating e to the 2x minus 3, okay? You can do one of two things. You can either just appeal to this rule, right? If it's in your head, that's fine. I do believe it will be on your reference sheet that you've already seen once before. So you can use that if you want. Just personally though, I actually prefer a slightly longer way, which might seem less efficient, but I'll try and justify why I like it in a second, okay? What I like to try and do is get this in this form, okay? I want to try and get the derivative out the front. I am really doing a reverse chain rule, so I want to make the chain rule obvious. So what I'm going to do is I'm going to write this as the integral of 2 e to the 2x minus 3 with respect to x, right? There's that f dash e to the f of x. But of course you can't just multiply things by 2 just because you feel like it, right? So to make sure I haven't actually changed this term, to compensate, I multiply by a half at the front. The half and the 2 mean there's a net change of, there's no net change, okay? So now that I've got that there, the half is outside that process of integration, right? That 1 over 2, that's the 1 over a. That's where it comes from, okay? And then this is going to become e to the 2x minus 3 plus my constant. Are you happy with that? Now the advantage of doing this, the reason why I try and do this is because if you get in your head, oh, it's chain rule, well, reverse chain rule, then when you meet things which are not just, oh, it's another rule, you will be more well equipped and will be more in your brain. So for instance, right, here, I'm not just having a number up front, I have a whole function, right? What function do I want here in order to be f dash? I want 2x, don't I, right? So as it happens, the numerical stuff here is the same, right? I want 2x there, that's the f dash I'm expecting, e to the x squared plus 1 dx. But to compensate for the 2 that I've unceremoniously inserted, I will multiply by a half, just like I did before. So now that f dash, that whole piece, it disappears when I get to the integral, right? So all I will be left with is a half e to the x squared plus 1 plus my constant, okay? And just to satisfy myself, let's just differentiate and double check, right? A half e to the x squared plus 1 plus the constant. What happens? This is chain rule. What do I do? 2x, the derivative of this guy, comes out the front. 2x, right? And then that's the inside function. The outer function is an endoparallel. What happens when you differentiate one of those guys? Nothing happens. He just becomes his same old self. And of course we know what happens to the constant. Cancel, cancel. There is the integrand, just like we were hoping. Okay? Does that make sense? Now admittedly, I mean simple examples to begin with, this guy here, this is the thing you're looking for. If you see f dash in there, you know, oh, this came from chain rule. Sometimes it's reasonably obvious. Sometimes they'll literally just hand f dash to you. Okay? More often than not though, you sort of have to muck about a little bit to make f dash exactly what you want, and then off you go and integrate. Question?
So what happens if it's like, if they give you more than the f dash?
Okay,
So
so it kind of depends on what kind of more it is. So for instance, let's suppose if I had this. Here's another example. This is a good example of more than, okay? So it's like, I knew what I was expecting out the front. I didn't get what I was expecting. So well, what do I do with this, okay? Now, interestingly, just because I thought up of this example, at the moment, you are not equipped to deal with this fully, okay? Because watch what happens. I want to get towards something I can integrate. This I know how to integrate, right? So I'm going to separate some things out. I'm going to do this. I'm going to say, well, there's this guy, right? And then there's this guy. And they're both being integrated. Are you happy with that? So that's good. This is a problem I already know how to solve. And then you would tackle this guy separately. Okay? Now just at the present moment, we don't have the techniques yet. We haven't developed them yet to deal with this guy on his own. Because he doesn't fit into any of the things that we know already. There's no thing out the front which is even remotely close to f dash. So you can't multiply by an x and then divide by an x out here. That's variables. You can't muck around with those the same way you can with constants. Okay? But this is the strategy I would take. If you've got extra stuff in there, then you better get that extra stuff out of the way so you can find the bits that you need. Okay? It's worth mentioning, you sometimes get the reverse problem. You sometimes think, I don't have enough stuff in here, and you have to do that trick where, just like when you have something like this, and we say, how do you rationalize this? Yeah, you have to insert something that is completely not there, and then it just all comes out in the wash. Sometimes you have to add something in that is not there. Those are harder examples. We will get to them in time. Okay? Essentially, though, at the moment, we're looking for something that will be fairly easy to transform into what I'm after. All right?